for today, actually. The afternoon is off, I think. Right? And so I think we'll start with two talks. I think the first one is from Alison, here from UC Berkeley. And after that, we'll have a break. And after that, another talk and a panel session. So Alison, thank you very much.
Okay, great. Thank you. Let me just get my phone to make sure I have the right timing in this. And we're going to do the discussion as in the panel discussion, right?
Yes. Yes.
Okay, great. Okay. Okay, well, thank you all very much for having me. I gather this morning is social science morning, and you may wonder what, in particular, a psychologist and a developmental psychologist like me is doing, thinking about the kinds of abstract questions about causal inference and intervention that are the focus of this meeting. And really, the project that my collaborators and I have been involved in now for a while, really almost 20 years overall. Sorry, let me. There we go. Is part of this general problem of trying to design intelligent artificial intelligence systems. And one of the ideas that goes all the way back to Alan Turing in that famous imitation game paper in 1950 is that instead of trying to produce a program that simulates the adult mind to try and design intelligence, perhaps instead we should be trying to produce one that simulates the child's mind. And the reason why Turing says this is because children are the best learners that we know of. And we have good reason to believe, and I think have had even more good reason to believe in the past AI spring of the past little while, that it's those learning abilities that are really going to be, going to define an intelligent system. So what my collaborators and I have been doing is trying to get cues for understanding how you can get an artificial system, a computational system to learn from looking at children and vice versa, trying to understand how it is that children, who are the best learners that we know of in the universe, can learn so much by figuring out what kinds of computations their brains are doing. So that's been a big project that we've been involved in now for 20 years. And one of the first ideas that we had was that one of the kinds of learning that seems to be extremely important, both for children and for computational systems, is causal learning. So figuring out the causal structure of the world. And in fact, if you look at the contrast between what current AI systems can do in spite of their great capacities and what children can do, you see that there's a pretty big contrast. So if you look at the kinds of things that you see in deep learning and reinforcement learning, in supervised learning, you need lots of data, and that data is typically supervised. Someone's giving you extra pieces of information like labels about it. And often there's not much or the right kinds of generalizations. So even if, say, ImageNet can distinguish between cats and dogs, to give a famous example, it doesn't generalize in the right way to novel instances or novel examples. And on the other hand, it's computationally tractable. We actually know how to do it. If you contrast that with the way 2- and 3-year-olds learn, and this is based on the data that I and other developmental psychologists have worked on for the past 30 years or so, what you see is that 2-year-olds with much less data and very different kinds of data than typical AI systems have, nevertheless make excellent generalizations from just a few examples. And as we'll see in a minute, one of the ways that we've tried to characterize this kind of learning is as a kind of Bayesian search through a hypothesis space. But the problem is that in order to do that, they seem to be able, what they seem to be doing is searching through these very large high dimensional spaces of hypotheses. And we don't really have an idea about how it's computationally tractable for them to do that. What kinds of things could they be doing that would be helping them to solve those kinds of problems? So we have AI systems that are computationally tractable, but seem to have these limitations. We have kids who don't have these limitations, but we don't have a good tractable way of describing what it is that they're doing. And for the past 2 or 3 years, my colleagues at Bayer here and I have been involved in a program from DARPA, the Machine Common Sense program. And I discovered that a lot of being funded by DARPA is about finding the right acronym. So the acronym for our particular project is MESS, appropriately for children. And MESS stands for Model Building Exploratory Social Learning Systems. So we think some of the things that the kids are doing that the current AI systems are not doing, that are enabling them to learn so much, to generalize so well from small amounts of data and so forth. The first one, which is very relevant to this group, is that the children are actually learning abstract causal models from statistical evidence. So they're not just looking for patterns of correlation, they're actually extracting abstract causal models in many of the ways that people have been talking about in this workshop. But the second part, which is where the interventions come in, is that they're also doing active learning, particularly through their exploratory play. So rather than just sort of sitting in their mainframes waiting for data to wash over them, they're actually going out and actively performing interventions on the world with the goal of getting information and being able to design abstract causal models. And the third part I won't talk about is that they're also learning in a social context. So let's take the first part, which is about the children, inferring causal structure from statistics. As I say, we started this work, it was a collaboration in particular with Clark Limor now 20 years ago. And it really came out of work that we had done earlier, looking at what we call the theory, the idea that children's cognitive development could be understood as something like theory formation. And of course, part of the reason why philosophers of science like Frederick and Clark are interested in formalizing causal inference is because causal inference is a deep, important part of scientific theory formation and part of scientific work, as everyone here can testify. So what we did was have a research program in which what we would do is present children, 3-4-year-olds, even younger sometimes, with patterns of data, statistical patterns, and then see what kinds of inferences they could make about causal structure. And I'll show you in a minute the way that we do it. You might ask, well, how on earth can you ask those questions to 3-year-olds? And what we discovered was that 4-year-olds and younger can rationally, normatively do things like infer whether a causal structure is a chain or a common effect or a cause by looking at the conditional probabilities of causes and effects. They can override prior causal knowledge in the face of new evidence. They can infer unobserved causal structure. They can apply this kind of inference across the range of sciences that we're hearing about in this workshop. So they're intuitive physicists, and here we're separating out the physicists and biologists and social theorists, but the kids are doing all of those kinds of science, and we can show empirically that children are using causal inference to do all those kinds of science. And interestingly, in our most recent work, including social inferences about how groups behave, they can infer and use counterfactuals, one of the hallmarks of causal inference. And as we'll see in a minute, they can infer abstract over hypotheses. So if we give children data to an amazing, I must say, in a way that I would never have predicted 20 years ago, they turn out to be incredibly good at making causal inference from various kinds of data, and they do it in a sophisticated way. Let me mention the most recent work that we've done along these lines. These are two, I think, brilliant papers by Marielle Gadou, my ex-graduate student, now a postdoc at Harvard. And here's two problems that have been really challenging for causal inference. One of them is, how do you identify causally relevant variables in the first place? So among all the variables, how do you even see which ones are going to be relevant to causal inference? And another one is, how can you reason analogically in a causal context? So if you see one cause leading to an effect, often, again, classically in science, what we do is say, okay, this is the way that water waves work, so let's see if we could take that causal structure and apply it to light waves. And what we showed was that even very young children, 3- and 4-year-olds, could use difference-making ideas to identify the causally relevant variables. So if you gave them a set of data that suggested a causally relevant variable, the kids would pick out the right ones. and also that they could understand abstract reason relations and reason analogically in a causal task. And it's kind of interesting that the conventional wisdom had been that kids are very bad at reasoning analogically. People in general are not good at it. But it turns out that if you give them a causal context, they're actually extremely good at it. So I'll just flag those two cases. But to get back to interventions, so that's the part about showing that kids are very good at abstracting causal models from data. But one of the other things that we found, we and others have found, is that children explore. And I can remember when Clark and I were first starting this, research program. One of the things that we discovered was that a big problem for us empirically as developmental psychologists was keeping the kids' hands off of the machines that we were using to test their causal inference. So if you gave them a causal problem, the first thing they wanted to do was go in and mess around and play with it and try and figure out how, for instance, how the machine worked. And I remember saying at the time, maybe this is a clue. The kids are telling us that the real way that you do causal inference isn't by sitting and getting lots and lots of large data sets. The real way you do causal inference is by doing experiments, by going out and actually intervening in the world and seeing the outcomes of your interventions. And by now, in parallel with the work that we've done, there's a substantial body of papers, and here's just some of the examples, showing that children will do this very naturally and spontaneously. And they don't just do it in a random way, they do it in a way that seems to be designed to give them some of the information that they would need to make causal inferences. So for example, in the work that my ex-students, Laura Schultz and Elizabeth Bonowitz did, they showed that children are more likely to do interventions when a causal system is confounded. And in work that Azura Ruggieri and I did, we showed that children are more likely to actually intervene to play and explore in situations in which the exploration is going to be helpful for solving causal problems. So all of these studies show, I think, pretty systematically that when children are playing, they aren't just doing it sort of at random, that they're exploring in situations in which they're likely to get more causal, more appropriate causal information. So what they're doing is actually intervening in order to be able to get information. And in fact, I think there's a good argument to be made, and I'll give you a little bit of data about this, but I've been making the argument more generally, that these exploratory interventions are actually characteristic of children in particular. So it's not just that children can do this, but it is what children do. And this goes back to, the classic explore-exploit problem. If you're trying to do various kinds of learning, including causal inference, you're faced with this problem that you could, for instance, quickly find a causal hypothesis close to what you already know, but you can be stuck in a local optimum where there's actually a better causal hypothesis, but it's further away from where you currently are. And you're always going to have this trade-off between using your causal inference to actually do things out in the world, which is kind of the thing that we often think about when we think about causal inference, and using your interventions to actually find out more, to get more information. So if you're in a causal context, you can either intervene to get the outcome that you want, to get reward, for example, as in reinforcement learning, or you can intervene to try to get information that will help you to understand more about causal structure. And what I've argued, this is in a paper that's in Philosophical Transactions recently, is that you could think of childhood as really being a way of resolving these explore-exploit trade-offs and doing something like performing simulated annealing. So the idea is that childhood, from an evolutionary perspective, is a period when you are allowed to explore in a wide-ranging way. And then in adulthood, what you can do is take the information that you've gained as a result of those kinds of causal interventions and then use it to effectively produce causal effects out in the world. And this is connected with the fact that if we look across many, many different kinds of creatures, we see that a longer childhood is associated with a larger brain and with smarter and more flexible kinds of performances. So if we really wanted to design an intelligent AI, one of the things that we might want to do is take a cue from evolution and give it this developmental structure of an early period of exploration in which you don't have to do as much, and then a later period of exploitation. And my slogan is that childhood is evolution's way of performing a kind of simulated annealing. And if you think about childhood and childhood activity from that perspective, then many things that look like bugs from the exploit perspective, things that you might think are characteristic of children, but look as if they're problematic or in the past have been seen as signs that children are irrational or that children are not very effective at causal inference. Many of those things turn out to actually be features from the perspective of trying to think of a system that would be very good at exploring. So for example, I think one of the biggest questions that is still an open one, I don't think it's been discussed much at the workshop, but maybe we could do a little bit of discussion in the panel about this, is how much does noisiness or variability of randomness in the kind of interventions that you perform actually help you to explore the space in a better way? And in the reinforcement learning literature, for instance, there's a contrast between random exploration and directed exploration. But I think, in fact, what you're seeing in children is this interesting combination. As I said before, there's a lot of studies that show that children are not simply randomly exploring, but on the other hand, they do seem to be have more random exploration than adults do. And things like risk-taking and impulsivity are examples of behaviors that might seem irrational from the perspective of exploitation. So you might think, why, if I know that a cause is going to lead to a negative effect, why would I intervene to bring about the cause? But if I'm simply trying to get information about causal structure, that might override your impulse to avoid risks. And things that are, kind of characteristic features of children in childhood, things we sort of take for granted, like the fact that children are playing rather than working, the fact that children are insatiably curious, even at the risk of their well-being. Those are all things that we might very well want to have in an exploratory system that's going out and intervening. And I can remember one of the first conversations, I think Frederick was there, it was at the one of the formal epistemology workshops, asking a question which I think has still not quite been answered, although some of the work on soft interventions and so forth might be speaking to this, which is, we have an idea from the experimental design literature of what an ideal experimental design might look like. But of course, those ideal experimental designs are very computationally intensive. They're computationally expensive and hard. What kind of approximate asymptotic heuristic system could you have that would be less than ideal, but that would still get you the right answer a lot of the time? And I think that might be what we're dealing with when we're dealing with the kids. Okay, so let me go back a little bit to this question about, well, how would we ever ask these questions? And one of the ways that we ask these questions is with this very simple device, the blicket detector. The blicket detector is a little box, and it lights up and plays music when you put some things on it. When you put some things on it and not others. And this is actually a 24-month-old, a 2-year-old in this experiment. And then the question is to try and figure out what things are going to make the box, light up. So the way we set up these experiments is, here's my machine, and some things make it go and other things don't. And your job is to figure out what makes it go. And then in the end, we just ask the kids, can you make it go? And with this very simple device, we can actually ask pretty sophisticated questions, and other ones like it. We can actually ask some pretty sophisticated questions about children's learning. And let me give you one example looking at this kind of using this device to look at children's exploration. This is a paper that just recently came out. And to do this, we combined our blicket detector task. We put it in the context of a reinforcement learning task. So now this is causal inference where there's an outcome, there's a reward. And here's the way the task goes. We're using an approach avoid task. So you have my blicket detector, and depending on what happens with the detector, you're going to win or lose stickers. So you see first of all, you get to choose whether to test objects or not. So you get to choose whether to put them on the detector or not. And if the object is a ZAF, then you get a sticker. But if the object is not a ZAF and you put it on, then you lose 2 stickers. So there's more of a loss than a gain. And then the question is, what should you do in terms of trying the blocks on the machine? All right, so now you've seen these 2 blocks. You guys can try and do this experiment in your own head. Now you've seen that the spotted one is making you lose blocks. You might think now you see one that has black stripes on it, and you try that one, and it turns out that that one is a ZAF, and it gives you an extra sticker. Now the question is, now what happens when you see this one that has black spots on it? Should you try it or should you avoid it? Well, if you've already made the hypothesis that that the rule is that stripes are ZAFs and spots aren't, this simple one-dimensional hypothesis, then you should simply avoid the black spotted block. And the trouble is, of course, if it's a more complicated, less obvious causal principle, in this case, the causal principle is that everything except the white spots is a ZAF, then by avoiding that block, you're going to be foregoing reward that you could have gotten. And work by Todd Garekis and others in the adult literature suggested that this is in fact what adults do. So if you do this kind of experiment with adults, what happens is they get caught in what's called a learning trap, where they never find out that the possibilities of the negative option. And this isn't just a theoretical thing that happens to people in the lab. It's something that seems to underlie things like anxiety disorders. So, you know, I get on an airplane and I have a terrible time. It's full of turbulence and I'm sick. And then I never get on an airplane again. I get the airplane phobia. But of course, as a result of that, I never learn that most of the time this is actually going to be okay. And if I had actually approached the situation, I would have found out about it. So as I say, this isn't just a theoretical problem. It's actually a real problem in many different kinds of circumstances. So what we did was just set up this kind of approach avoid task. And then what we did was we did it with different ages, 4-year-olds, 6-year-olds, and adults. And we saw, first of all, how much did they approach or avoid the tasks. And we found that adults, just as in the previous experiments, in fact, were avoiding blocks that were potentially rewarding. And they were doing that more than the 6 to 7-year-olds. On the other hand, the 4 to 5-year-olds, if you know 4-year-olds, this will make sense to you, were continuing to approach. Although they were sensitive, as you can see in that second slide, they were sensitive to the negative reward. Their impulse to try to put the blocks on the machine was much greater than that of the adults, even though we showed in various control conditions that they knew, or at least they predicted, that it was most likely that they were going to lose reward, but they kept experimenting anyway. And interestingly, when we then asked them what's the causal principle, so now we're trying to see if they've learned this unlikely causal rule, what we found was that in fact the children were better at learning the causal rule than the 4-year-olds were better than the 6-year-olds, who were better than the adults. So this trade-off of wanting to get more exploration, doing interventions even when you thought that the outcome was going to be negative, but when you thought that you might get some information from them, this was actually, especially in the children, that was actually leading them to be better at causal inference in a situation in which the causal relation was had a low priority to begin with, was not obvious to begin with. And that might, again, if you're thinking about, you know, artificial systems, this is a particular way of resolving that explore-exploit trade-off. And in fact, you know, the kids got less reward at the end of this particular experiment, but one's assumption is that by getting the causal inference right, in a broader sense, in the long run, that's something that would enable them to have more reward. Oops. This is wrong. Oh, sorry. Well, I'll have to go back to this. Okay. Now, the experiment that we're doing right now, in those cases, we're talking about relatively simple causal inferences about whether something is a blicket or not, makes this go or not. But in other experiments that we've done, we've shown that children can also infer more abstract kinds of causal structure, what people sometimes call over hypotheses, more abstract ideas about how a causal system works. Here's an example of this kind of experiment. We've done this and replicated this a number of times now. So you see a situation like this. You have blocks on the machine. D goes on 3 times and nothing happens. E goes on and nothing happens. The combination of D and F go on and the machine lights up. And the question is, are they blickets or not? Now, if you make the usual assumption, which is that this is a disjunctive causal system, if your over hypothesis is that the functional form of this is disjunctive, then you should say that D and E are blickets, but sorry, that F is a blicket, but D and E are not blickets. And that's exactly what adults say. But if you first saw this other sequence, this second sequence where it says conjunctive training, where you saw that A, B, and C don't make the machine go, A and B together don't, B and C together don't, but A and C do, then that would give you a clue that maybe this machine works differently than you thought. Maybe this machine doesn't work on a disjunctive principle. Maybe it works on this conjunctive principle, that combinations of objects are making the machine go. And so what we did was we simply gave people of different ages either evidence that the machine worked in the obvious disjunctive way or evidence that the machine worked in this less obvious conjunctive way. And the question was, would they use that? Sorry, they saw a machine. So they saw different blocks in the disjunctive and conjunctive case. And the question was, would they generalize from those examples to make an inference about the new blocks in the machine? And what we found was really interesting, which is that if you looked at the case where there was no evidence at all, or the evidence was for the likely disjunctive hypothesis, there was a little evidence that the adults were more likely to go for the disjunctive evidence than the kids, but everybody kind of showed a preference for the disjunctive hypothesis. On the other hand, if you looked at the conjunctive hypothesis, you saw a really striking developmental difference. So even though the adults were more likely to have the conjunctive hypothesis when the data supported it, they were still more likely to choose the disjunctive hypothesis. Whereas the children were much more likely to actually weight the evidence appropriately in choosing the conjunctive, the unlikely hypothesis over the more likely hypothesis. And interestingly, there seem to be some striking transitions exactly at points that we know when we know that, for instance, there are brain changes in brain structure at this transition from preschool to the school age, about 6, and in adolescence. So now, in the few minutes that's remaining, let me tell you about, and in a sense, this also is suggesting this kind of idea of the young children being more exploratory, but this is not about the children's actual interventions to try and get data. This is about the way that children seem to be searching through the hypothesis space. So in this case, what seems to be happening is that the younger children, the children in general, are looking through a wider hypothesis space, considering a wider range of different options, sampling more broadly, and we think also sampling at a higher temperature than the adults are. So the last experiment, which is the one that I'd really like to get some feedback on, maybe in the panel discussion, we wanted to, what we're doing right at this moment, and we're presenting this at the CLEAR conference on causal learning and inference that's coming up soon, is to try to see whether we can, would children be able to learn this abstract structure in the context of their active exploration and interventions, and are they going to produce interventions that will help them to learn this abstract structure? So what we've done, this is part of a very general research program that we have, which is trying to use virtual environments to give kids and agents exactly the same problems. So instead of actually having a real blicket detector that we put objects on, instead we have this virtual environment with different kinds of objects and the detector. You can put them on the detector, and then you press that check button and you find out whether the detector is going to light up or not. And the first thing that we've discovered is that 4-year-olds are very happy and willing to intervene and play with this interface. So the interface is set up so that you can use your finger to move the objects onto the detector. And what we've done in this experiment is we've given them 2 different conditions. In one of them, they're actually given the potential hypothesis space. So we show them some machines work on a disjunctive principle, some machines work on a disjunctive principle. So in the one where they're not given the hypothesis, they get this ambiguous evidence. In the one where they are given the hypothesis, they get unambiguous evidence for one or the other. Sorry. And then what we do is simply let the children play. So we just let them intervene for a space of 3 or 4 minutes, and then see what kinds of interventions they make, and then at the end, what kinds of inferences they make about the causal structure. And we're comparing this to various kinds of learning algorithms, particularly various kinds of reinforcement learning algorithms. And we're still trying to, part of the challenge of this is trying to actually do the analysis, make sense out of what the kids are saying. But what we can, and again, if people have some suggestions, that would be great. But what we're finding so far is that the kids are making the right kinds of inferences. So simply by intervening on this object, they're ending up figuring out whether it's conjunctive or disjunctive. They make different inferences when you give them the hypothesis space or when they don't have the hypothesis space. And so far, the biggest difference between what they're doing and an ideal intervener is that they seem to be trying a wider range of hypotheses than just the ones we give them. So they also seem to be trying a hypotheses like that the object might be stochastic, or even that there might be a negative inhibitory effect of the objects. So let me end by showing my collaborators on this. That work that I just described is collaborating. It's really Eliza Causal is the person who's done the most work on it, but also collaborating with Rosemary Key and also Jessica Hamrick. And we are trying to, what we want to do is think of this as the first pass in trying to look at the kind of spontaneous exploration that children do and use that as a cue for how we could have ideal causal interventions in an artificial system. So thank you.
Thank you for the fascinating talk.
It's a very quick one.
Yeah, so quick question.
Yes, what was the title of that last paper? Could you say that one more?
Oh yeah, the last paper is, it's learning causal over hypotheses through exploration.
Thank you.
Let me